Hello, and welcome back to yet another compiler stream. So, I'm pretty excited for today's stream because today we will be implementing type checking. So, we'll be actually validating that like our program works correctly at compile time and not just throw an error if, for example, there is an integer used as a boolean expression, which is pretty cool. So, but to wrap up, what have we done in the last stream? So, in the last stream, we have added support for declaring functions and calling these functions. We have also added an optional main entry point. So if you specify a main function in your code, that's where the program will start. So if I run this program right now, it will just do nothing because there's nothing in here, even though there's a whole lot of top level statements here. So I see that. Blah, blah, blah. Yep. So result none means nothing was executed. But if we just now remove this main function, we should see 20 as a result. Yeah. So I think that's pretty cool. And right now our functions are pretty dumb because we do not validate return types, parameter types, and stuff like that. And you can even put like statements after the return. But we will fix that in later episodes when we introduce more advanced concepts. Yep. So what's the plan for today? Today we will implement type checking. And with that comes a lot of refactoring actually. So we will refactor a lot of the AST related code because we will move away from our current approach where we just store everything as a tree structure. Because right now, if we have, for example, a statement, wait, let me just show that to you. Like, for example, we have a union expression, we have a nested expression in here. And that makes it kind of hard to do type checking, actual lookups and stuff like that. And because of that, we will introduce like a node ID for every expression and every statement. So you can efficiently look up any node at any time in the tree by just calling a function on the AST with the node ID and you get back the node. And that also makes it a lot easier to like mutate these nodes and assign types to them in Rust, because passing around references in Rust with lifetimes is kind of a pain sometimes, especially with the borrow checker and stuff like that. So I like to just have one point where everything is like managed, like all of the nodes and stuff, and you can mutate them there. And so we also prevent like multiple statements being cloned and stuff like that. So we don't have any duplicates and problems with like we mutate the wrong memory location and then the original statement was not mutated, but the new one that we have created with clone is mutated, and like we just prevent data inconsistencies. So I mean, we could just start actually, I suppose. Yep. So let me just set this up real quick. Cool. So I think we might be ready. So yeah, first step is we need to introduce some kind of ID. So how will we do that? We'll probably say something like, okay, we have a struct called AST, it's like statement ID, which will hold an ID, like a usize probably. Actually, we could just make it a U32 for now. And this will derive from debug clone and copy, because we actually want to be able to copy this because it's a wrapper around a single integer. So that's fine if you copy this. Constructor for that. Now, I thought about it a little bit. We could also introduce like just not separate IDs for statement and expressions, and just have it like a node ID. and introduce a new type called like an AST node, which just could either be an expression or statement. But I think that would make things kind of hard because in our we currently don't have the use case that a node can like be an expression and a statement, right? So if we have an ID, we know exactly that we either want a statement or an expression. So it does not make sense to unify those because that would just make the code a little bit more messy. So now we need another ID called the AC expression ID. And now we need some kind of way to generate those IDs. So we'll have like an, I don't know, AST node ID gen, which will just hold the current statement IDs. And we want those to be like, we want this struct to be accessible like with a immutable reference. So we use our contrast struct, which we have created in one of the last episodes, which just holds a cell of usize. So if I think about it, we'll probably have to change that to usize then, which is fine. Cool. And now we will provide the implementation. Right. So yeah, I guess that's not quite correct. Like we could say like that ID is equal to current value, and then we just say next, or I think it's increment actually, increment. Yep. And then we just return a new statement ID. We're gonna do the same here. I mean, it's actually like duplicated code. I guess it's not that tragic because it's just 3 lines and it's fine for now at least. And we'll have some changes in here because we won't just store like top level statements here, but instead what we will say is we'll say statements, and this will actually be a hash map of like our statement IDs to our statements. Same for expressions, and we'll have a node ID gen, and like probably we'll see that later what else we need. So like statements will be hash map, expressions will be hash map. We need a new node ID gen, I guess. And yep, probably should also like derive quality, partial quality, and hash here. And now let's get started with migrating. This will be a little bit boring, I suppose. So what we need to do is we need to like basically replace every reference to an AST expression with just an AST expression ID, right? So we have to change this. We have to change this to an AST statement ID, and now we can actually get rid of all like the boxes and stuff, which is pretty cool as well, I guess. So we'll replace the expressions first. So we'll take an expression ID now. So will you, and no box needed anymore. So same here, no box needed. Do we have anything else? Yep. No box needed here as well. So will be an expression ID now. This will be an ID. I think it has it, I guess, yep. Now we have to replace the statement IDs or statement references as well. So let me just copy that. So replace that, replace that, replace that, replace that, statement ID. So do we have any references elsewhere? I don't think so. Okay. So we have done that. And now because we have a node ID gen here, right, we have to provide IDs for these, we have to probably move these constructors out of the actual AC statement and move them into the AST struct. So let's just copy these, right? And okay, of course, every statement also needs to have an ID. So we should not forget that. So otherwise, it wouldn't make any sense here. Where is our AST expression? Struct AST expression. Thank you. And you will need an ID as well. Cool. And so now in the constructor, we'll probably also need to provide an AST expression ID. Okay, it's working. Cool. Same here. AST statement ID. We'll just pass right here. And now I've still copied all the constructors, so we can just put them in here. And we'll rename that one to like expression statement. And this will take, will it take that one? I don't think so, right? I think we will take IDs here, right, straight away. So expression ID and expression ID. Do we need to say clone here? Expected struct AST found statement. Oh, because we tried to return self from here. Okay. I guess what do we need to do here? I think what we could do is we could like write ourselves a little helper method called like statement from kind, where we just pass statement kind and return this, just generate a new ID, right? And what we can actually say here is, okay, we need this ID, and we can say statement from kind. This needs to have a reference to self, I guess. Cannot borrow, yeah, is mutable next to ID. Why do you need a mutable reference? That's not correct. So now this works. Cool. And now we can just say like self. Okay, so we need reference to self here. And probably even mutable references, right? Because we need to create this statement. Like that statement, and we need to insert it, right? So we need self insert and return the actual reference. So now we can say we also want to return reference to the newly created statement here. Just say self statement from kind. Cool. So let me just adjust all those return types, I guess. Cool. So next up, our let statement, which will now take an ID as well. So that's what I really like about Copilot, like, right? Because before what I had to do is I had to like rewrite the whole stuff, like copy it and paste it. Now I can just remove it and it will just remember what was there before and just write it in the correct way again, which is pretty cool. So we have to replace these as well. Correct. So we need mutable reference everywhere. So I guess we can just paste this everywhere. Yep. You will need a statement ID back. Should also be an ID, right? You should be an ID as well. So ID as well. And you will need to be an ID as well. Cool. So let me just check if the stream is working. Yep, fine. Cool. Okay. So now we have done this. Actually, probably won't even need this add statement method here anymore. Cool. And now probably the same thing for our expressions, right? So let's just take all of those from here and move them in our AST struct. So we can rename that to number expression, I guess. And we'll need a helper method here as well. Expression from kind. Yep. Thank you, Copilot. Appreciate that. So, and we'll need mutable references everywhere here as well. So let's just pass those. Blah, blah, blah. Okay, cool. I'll Copilot, do your thing. Nah, expression from kind. So, yeah, I think he's got it. All right, let's change those return times as well. Beep. Nice one. Okay. So this will need to be an expression ID actually. Same here, same here, same here, here, and here. Okay, we don't need boxes here. Okay, wait, what? Okay, that's weird. Identifier. Wait, that's variable, right? Yeah, it was variable. Okay. Assignment, expression, boolean expression, call expression, error expression. So now we'll probably have to rename those. Okay, I'm being called. Okay, be right back. So I'm back. Cool. So next step will probably be to fix our visitor, because as of now our statement, like visit statement function, takes a reference to an AST statement, but now it has to take a reference to an actual node ID, right? So to fix this, we have to change this. We have to say like node, like statement ID, and we'll have to change that as well in here. No, that was kind of wrong. Visitor, so please, nice. Okay. And next up, what we probably need is something like a query method on our AST, right? So we have to say like have a query expression and query statement. And now we also need a method here like get AST. And we probably even don't need this lifetime here anymore. We can remove that, which is unnecessary. And we can say that statement is equal to like self get AST query statement and clone. Yeah, we probably need to clone that, which is fine because now we can clone statements whenever we want, because we won't clone like the entire tree, but more like maybe 8 bytes, because we have like 2 IDs in there, which is fine, I suppose. And now we can visit the expression. Yeah, and we have to change that as well. So now we have to take an expression ID here, and so here, and we'll have to query the expression here. Cool. That's working. Did we just fix our visitor in like 2 seconds? Nice one. And now, okay, that's actually like a bug at the moment, I suppose, because we just visit like the statements, and statements just contains everything, right? Like every single statement we have ever allocated, but only want to visit like top level statements. So we need to have like another, like a vec of top level statements. And we can say like pop fn mark top level statement. Yep. And now we can just say itself top level statements. And now the visit method works as expected. Please learn to talk, lol. Top level statements, like new, correct. We don't need you anymore. We'll probably need, yeah, we'll need an actual reference to an AST here. Let's see how we will get that. So probably AST here. We can just move the AST, right? Or we don't even need to clone that. And if we have a reference to the AST, we can just remove that from here and say, okay, we'll just use our own AST. Right, okay, cool. So that's working. Now we don't need this lifetime here, I guess. Found, okay, and we have to change our function symbol to not take a statement anymore, but take a statement ID. Yes, yeah. So we don't need you anymore. Expected AST statement, found AST statement ID, yeah, which is correct. Nice. Let's rename that for good measure, function body ID. And we'll need the get AST method here. So we will probably need a reference to AST in here, which will need to be passed in here. So AST, ST, Okay, we need lifetime here. And now we can just return this. And we'll probably need lifetime here as well. Do we? I don't even think we do, to be honest. So same thing for our resolver probably. We also need a reference to the AST here, which we'll also need to pass via the constructor. And we'll need lifetimes here. Cool. And now we'll need to borrow the AST here. And so we do here. And yeah, we don't need a lifetime here. Cool. So next up will probably be the parser, right? Okay, now parser the AST printer, which will also turn just a reference to its own AST. So we need a lifetime here. Right. So AST, AST. We need a lifetime here. Cool. Expected statement. Wait, what? Okay, so that's still not correct. Correctly overridden. Okay, cool. That works. For AST evaluator. Okay, so we probably need a reference to the AST in here as well. Cool. Reference to the AST. Need that in our constructor. AST, AST. And I think now we're officially done with like passing AST stuff. Now we have to refactor this. Now we have to create these via the AST now. And actually our parser will probably need a reference to the AST as well. And actually like a mutable reference. Because we have to insert stuff in the parser. Cool. So we got this and probably change these to return references, right? Our statement, and we'll take the ID here. And now that's like the advantage of having copy as a trait for the ID. So we can just say this without actually transferring ownership, which is cool. Or without having to explicitly say copy a clone here. Which makes the code a little bit less verbose, which is always a good thing. Allow empty return statements, right. So self AST return statement. Change this return type. So let's just change them all, I suppose. It's always easier to do that at once. Same for our expressions. Our expressions will also return a reference now. Cool. So you will also return a reference, and so will you. Right. So this expression will probably also just need the ID. So we do here, and also for the condition. Statement, we'll also have to just push the ID here. If statement, so we just need to need the ID here as well. Same for this. Cool. ID here as well. ID here as well. Just the ID here as well. And I think we're almost done actually. right, binary. Okay, so this needs to be an ID. This needs to be an ID. This needs to be an ID. And we can just say self IC binary expression. And we probably have to query this now. Like self IC queries expression with our left ID. Probably need a reference here. Yep. Cool. So I think we're almost done. Self AST number expression. Okay. Probably clone the token here and just move it here. Right. So why do you even need a token? Okay, let's just take this token here. I mean, we can even probably adapt this and say token. Yep. Why not? So back to our parser. Now this should work. And that's not quite correct because we need to create a parenthesized expression here. Identifier expression. It's variable expression, I think. We need a boolean expression. And last but not least, an error expression with like the span of the token. So we just need to push the IDs here. Okay, I think we fixed our parser. So what's next? Okay, this is next. And now we need to pass an ST here. Can we just pass self? Okay, cool, we can. We need a mutable reference to our ST here. And this we don't need anymore. We can just say if we use parser like parse. Make a new method on our parser. We can just say, okay, parse. And this will just say while that's statement. Next statement. Okay, we need a reference to self here, probably a mutable one. Self next statement. Self AST mark top level statement. Because here we just parse the top level statements, right? Actually, do we? Yeah, we do. Okay, that's correct. And we'll need a reference to ST here as well. And okay, why do you not like this? Okay. I suppose, why could that be? Oh, okay, makes sense. I guess what we could do here is we could just say like map statement and map to the ID actually. Yeah, that works. Because now we have ownership of the ID because it's like shadow copied. Okay, so this does not work. Borrow of moved value statement, which makes sense. So we just have to extract this. Let's just say like ID, right? Same problem with our, yeah, with our expression from kind. Expression ID. Cool. And okay, I guess we just have to change the order here, yeah. And it works. Okay, cool. That was pretty fast actually. So we get 20 and do our test pass. Okay, we have some kind of error on our tests. So what is the error here? Okay. Oh, okay, that's actually annoying. I guess let's just say we just clone the AC here, which is fine because this is just a test and it will make this compile. AC will need, we need to clone that. You don't need hash and copy. Probably need to implement those traits for this struct. Okay. And for our counter, probably. So do you run now? Yep, okay. And every single test passes. So let's just add a test configuration here, I guess. Test, and this will just run carpet test. Okay, that is cool. So I'll drink something real quick. Staying hydrated is important, guys. Don't forget that. Okay, cool. So everything works as expected now. So I think we can move on and do some cool type checking stuff, right? So how will type checking work? So if we take a program like this, what types do we expect? So we expect this to be a boolean, right? Because there's a condition, and the condition value should be a boolean. We expect a to be an integer and 1 to be an integer, or at least like let these be two types be compatible over the plus binary operator, right? Which for now will only be available for integers. So the left type needs to be an integer and the right type needs to be an integer. And like every expression has a type. So this expression will have an integer type, but this expression will have a boolean type, right? But a will have an integer type, and so does 10, right? And if we wrote false here, that would be not correct, right? Because we can't compare false with 10. Like at least not without any like implicit conversions of false to like 0, which we will not do because that's not cool. And yeah, so statements do typically not have any type, right? They are just void, I guess. So we will not give them any type, but rather like every expression will have a type. So we can just say, okay, where's our C expression, and this AC expression will have a type. So like type. And we have to define this type now, which we'll probably put into a new module. So like maybe like typings. We'll add this. Cool. And like pub enum type. We'll have in for now, bool, and probably unresolved. So why do we need unresolved? We need unresolved because I don't want to have like an optional in here, right? But we need to have some like kind of default value for our type because we have to assign something to it if it's not an optional, right? And at the beginning, unresolved is actually like the true state, right? Because if we just parse the AC, we don't know nothing about the types, and we will assign them later. So we actually need type here. Type, and type needs probably to derive from debug and clone. And we will implement a constructor for type. No. We don't need constructors in enum, right? Okay, cool. So just leave this empty. But we will need to implement display. All right. Cool. So now has a type. And by default is boolean type unresolved. And now we will get to the fun part. So before we do anything, we can probably write some tests to ensure everything is working as intended, right? So we can say test should report type mismatch when int is used in if condition. Something like this. So we can try to implement something like that. Expected boolean found int expected. No. Probably like expected type boolean found int. I think that's a good error message, right? I guess that should work. So now this will probably fail. Yep. And now let's try to actually make this pass. So to do that, we will go into our resolver. And we will now have to change the types of the nodes when we visit them, right? So to make this test pass that we've just written, we need to assign a type to our number expression, right? So whenever we visit a number expression, we say we need to assign the type. So we need to get the ID here, right? So how do we assign a type? I mean, we could probably say like set type, which would take a mutable reference, an expression ID, and a type. Yeah, that sounds reasonable. Yeah, that looks good actually. Cool. And not some, like just type. Okay, and we actually have a problem here right now because we cannot get an ID from here from this number expression, right? Because it does not have an ID property. The ID property sits in the expression, AC expression struct. So what we need to do is we need to change our visitor a bit. So we need to also pass the original expression in here, right? AC expression. And yeah, we should probably just pass. Yeah, it doesn't really matter actually. I guess that just passes the original expression, AC expression. And we'll need to do that for like every expression. So let's just do that all at once. Probably not for the arrow, right? Okay, maybe. Yeah, maybe we do actually. Yeah, not for now. But for our parenthesized expression, assignment expression, call expression. Yep. Cool. And that's actually pretty simple because we have a reference to our expression here, right? So we can just pass that here. And just do that for every expression. And that's as easy as it gets, I suppose. So we should also do that for a Boolean expression. And now we also have to add that in like every visitor, which is kind of annoying. But it's fine for now. So expression, cool. So what we now can say is we have a mutable reference to our AC, right? Do we actually? I think we don't, right? Do we? We do. Okay. And expression ID. Okay, wait, this is not public. Okay, like everything is not public. We should probably make everything public. But we'll make that as we need it. The reference here. For type, we don't have a number type, but just an int type. It actually works. Wait, do we have it? Or do we own this? Wait, what? Wait. Okay, that does not seem right. Wait, what? Doesn't set type not take immutable reference? It does. Huh. Okay. I think we will probably get an error here later. But now it's fine. I don't know why this works. That's pretty weird. Right, same thing here. We just set the type to a boolean. And this should actually now make our tests fair. No, not just yet. We have, of course, have to like validate the types as well, right? So we need some kind of method like, I don't know, like expect type or type mismatch. So if like expect, we probably don't want to do that with like quality checking, because we could have implicit conversions from like int to float and stuff like that, but int is not equal to float type. So we probably need a like a method, like if actual is assignable to expected, like not, then we report a type mismatch. So type mismatch, we need this method in here and report type mismatch. Probably not take a token, but rather a hex span in here. Expected would be type. Actual would also be type. Expected type found. Yep. Okay, so this is also the correct message. Cool. We need references here. Probably this will already be a reference. And we'll need to implement this assignable to method. And is assignable to. Right, so with an int and an int, that's true. If we have a boolean bool, it's true. Otherwise, it will be false, because we don't, everything that is unresolved should not be assignable, because then something kind of went wrong. Right, because if a type is unresolved, then the children have not been visited of that expression, and that is not correct. So in the future, we'll probably also add like a void type, which we then can assign if there was an error, like when parsing an expression. I think Rust does that. Like if you have an error, like syntax wise, you just get a void type. And I like that. So cool. So now we can expect a type, and we have to expect this type in if, right? We can say, okay, expect type. What? So we expect a type boolean. Spool actually. And the actual type is, I guess we have to query this now. Let condition expression yourself a C query expression. Right, so we can say condition expression type. And we now also have access to the span, right? Actually, do we condition expression? Okay, so that's a problem. We can't pass a span here. So we probably need to a method like span, which will compute the span for every single expression, right? Okay. Yeah, let's do that. So we need to go into here and say like public and span, I guess. And we will just match self-kind. And we need to return like a text span here. And okay, so for a number expression, that's actually pretty simple, I guess. Just clone this. For a binary expression, that will be a little more tricky. Unary expression as well, parenthesis expression as well, variable expression, pretty simple. Boolean expression, pretty simple. Chord expression, also not that simple. And yeah, expression also simple. So, how is the span of a binary expression composed? Right, so if you have a binary expression like, I don't know, that a is 1 plus 2, binary expression, the span is defined by the start of the first expression and the end of the last expression. Right? So we have to compute this somehow. And we'll also have to do like the same for every other expression, like a unary expression, because this is also a valid unary expression. You can't just say, okay, like let's just say, okay, we take the length of the operator and stuff like that. And it wouldn't work. So what we can do is we can write ourselves a little helper method, like an I don't know, like compose spans, combine spans to take a reference to itself, and like spans, like just a vec of text spans, and return a new text span. So is that correct? No, it actually is not. So because these spans could not be sorted correctly, we have to sort them first, right? And we have to sort them by, okay, this is mutable, and we need to sort them by start. Okay, thank you, Copilot. That's actually correct. Yep. Start. Cool. And we now also need the literal string use, so we have to just loop over every span. And that is also why it's important that we sort this. So we now got the correct literal. Like actually we probably won't because spaces are not in there. Yeah, we'll see if we even need the literal. I don't even think we do, right? So we can just pass an empty string for now. Let's just leave the white spaces out. So start, restart, cool. And now we just need the spans, right? So self combine spans. So left will be okay. So we don't have access to the span here, right? So we need to recursively calculate the span. So we first need to do a lookup, which we can't because we don't have access to an AST. So we probably also need a reference to an AST in here. Yeah, you will see that a lot. Like we will passing around our AST a lot because it just holds all like the valuable information. Like, is there something like varg in Rust? I don't know. We could actually also make that an instant method of like text span, right? I think that would actually be a lot better. Yeah. Let's move this. Let's get this out of here and make that an instance method of, right, like a static method. And combine. Let's return a text span and we'll take a mute vec of text spans. Cool. And we'll probably also need the operator in here, like operator, expression, operator, token, span, clone. Cool. So we'll just pass the operator here. So same for our unary expression, right? Yep. For a parenthesized expression, that will actually be the same. And not quite actually, because we also need like the parenthesis, open parent. Will be expression, open parent span clone, close parent. Right. So we don't actually have those right now. So we need to add them. Like open. Like, let's just call it left parent because we have also done that in our lexer, and right parent. And we'll probably also need that for our call expression, right? We can do that if we need it. Okay, cool. And now for our assignment expression. Equals, we also need the equals token here. In our assignment expression, have equals, just be token. Wait, where are we? Help. Just implementing this method, right? Yeah. Okay. And probably also for our call. Identifier, like left parent and right parent. Cool. Left parent, span clone, right parent. And we probably also need like all of the parameter spans. Yeah. So let's just say spans. Yeah, exactly. That's what we need. Cool. And now we need to add left parent here. And left parent. And left parent. Right parent. Okay. Cool. So now our parse method should actually work. And we will probably only have to like pass those constructors. So we need like left parent, right parent, token, left parent, right parent. Same here, we need equals token. Equals here. Okay, now we need dot here. And left parent, right parent. Right, left and right parent. I think that's it. Maybe our test does pass now. Okay. Expression is T expression. We need to add that. Okay, here you go. Here you go. Stop complaining, please. Here you go. Okay, let's just rename that binary expression. And now we can add this. Okay, cool. Okay, same for this visitor, I guess. Blah, blah, blah. Okay, cool. I need to import this here. App. Okay, so this is done. Do you run now? No. Okay, so now we have to parse the tokens, or like store the tokens and pass them. So clone that equals. So same for our left parent, right? Our right parent. So our left parent will be token. So left parent expression, right parent, okay, that's correct. So probably same, exactly same like left parent. Clone. Same for our right parent, right? Cool. Now we have to pass this here. So now please run. Okay. I think we pass st. Okay, so now we get this error. Okay. So now we need its st to be a mutable reference, which hopefully will not be a problem. Please do not be a problem. Ah, shit. st is mutable. Okay, so maybe let's just say like resolve or resolve. So we can just take, because instead of using the reference from here that we have borrowed as mutable, we can just take the reference in the actual resolver to visit the tree. So resolver like resolve. Just say self ast visit. Okay. And I guess this won't work because we have borrowed st as mutable, so we can't borrow this as mutable as well. Okay, maybe let's just re-implement the visit method here. Like say like let statement IDs is equal to self st top level statements iterator, and we'll just map to statement IDs, and now we can like say resolve statements. Actually, we don't need to do that. We can just say for statement IDs resolve statement visit statement. Cool. Now test pass. Okay, what do you like this? Okay, so you need to type statement ID. Can I be? Oh, this already is a statement ID. Okay. Maybe now. And the test fails. How dare you? Expected. Oh. It actually works. It's just the wrong error message. So expected type bool, found it. So now you pass. And this is what we like. And now next thing that we want to do is like variables. So if we use a variable with a non-boolean type and if statement, so it should report type mismatch when variable of type int is used in if condition. Cool. Probably also can extract this logic into just kind of, okay, this is like bad. Why can I not extract this? Hello, please. Could say like assert diagnostics. Okay. So let's just do that, and let's just replace all of those with like a call to assert diagnostics input expected. Cool. So now we don't have to write those two lines everywhere. And wait, it didn't actually do that here. Okay, that's funny. Assert diagnostics. So we'll just do that manually then. And next test we could probably write is should report type mismatch when binary expression is if condition. Binary expression of type int is used in if condition. Right, because this should not work, right? Because this binary expression just returns another int. And next thing we could probably say is should report type mismatch when adding int with none with bool. Right. Expected type int found bool. So actually the error should not start here, like here. So now let's try to make these tests pass. Actually fail. Okay, and this fails as well. Okay, makes sense. So how will we do that? We'll get back into the resolver, of course. So what we have to do now is actually like specify the types for each expression. So for our variable expression, this will be the first thing that we can do. Like right now, I think our variables are just void, stored as void, right? Okay. So we need to change that to a variable symbol, which we can create just below the function symbol, variable symbol, to hold a name and a type. And a global scope will hold variable symbols as well. Let's just move this down here. So when declaring a variable, we can also define a type. Variable, right. Cool. And here we will return option of like variable symbol. Okay. Same thing here. Type variable, variable. And also change this. And now we can also have to change this method. Okay, and we will have to change the lookup method as well. So this we can keep, I guess, this loop here for scope and yeah, that's actually correct. Cool. So now when declaring a variable, we can just say type, yeah, parameter type, I guess. I mean, we do not have types for our parameters yet, so this will just be type unresolved for now. When declaring a variable, we will just take the initializer. Yeah, we'll just take the initializer type. Initializer expression, right? Okay, cool. Yeah, we just take this type. And now we can say, actually, take this expression and match against it. And say if we have none, we'll just paste this code, because then we have to report in undeclared variable, and else we can probably set the type for a variable expression. Cool. So how many tests are still failing? Okay, so one test is passing. So next up, we should probably do this. So now we have to do something with binary expressions. So what you can typically do here is like kind of have a table which like specifies which types are allowed for each binary operator, right? And like which type they evaluate to. So we can say like I don't know, like resolve binary expression or something like that. Yeah, I guess. So this would take me to reference to self. And probably like an operator, like left. Okay, let's see expression, right, I see expression and operator. ST binary operator, is that correct? Probably just need the kind here. So. And we will return a type. So what we can say is like something like left, like matrix will be of type, type. So the first two types are like left and right hand side, and then we will have the result type. And we will match on the operator. So we'll just say, okay, remaining patterns. So on a plus, we just have like int, of course. Same for minus, same for multiply, same for divide, power, with and as well, for or as well, for XOR as well, not for equals. Then we have bool, same for not equals, same for less than, same for less than or equal, same for greater than, and same for greater than or equal. And now what we have to do is we have to actually expect the types, right? We have to say self expect type. Like the expected is the int, and the actual is like the type of the left expression. And the span can calculate with the AST and our newly added span method. Cool. So this is working. Now we have to call this whenever we visit a binary expression. So visit binary expression. So we first have to visit our left and right. Right. So like let left. First have to visit this self-visit expression left. Expression right. Wait. Oh, left and right are not public. Okay, that's kind of a fail. Pub and pub as well. And right. And now we can say self-resolve binary expression. And here we'll probably just need left. Okay, left, right, and our operator will be our binary expression and operator kind, which is also not public. Great. Okay, and now this is type. Now we can set the type for our expression. And now the test will probably pass. Okay, it actually does not. We're failing more tests than before. Okay, why is that? Expected literal found. What? Oh, because okay, so the span message does not match. Okay. I mean, what we could do about that. The problem is that we're missing white spaces, right? And I guess we could just fill like missing spaces with white spaces. So because we have sorted them after start, or like by start, we can just say, okay, will keep track of the current position, and if the position does not match the end of the last span, then we'll just fill up the remaining space with white spaces. So we can say like let like I mean, do we have to even do that? Probably have to enumerate here. Enumerate like index span. Like I think that's some cool method. I don't know. Wait, how's it called? Where you can like also access to the last. Oh, not reduced, not change. I don't think it's fused. There's some cool method which also gives you access to the first, like the one before, the span before. Wait, let me just Google that real quick. Okay, no, that's not correct. ChatGPT. Let's move over iterator, element before, and current element. Something like that, maybe? Window. Yep, I think that's what I was looking for. Wait. Oh, wait. Is that what I was looking for? Huh. I don't actually know. Hmm. Okay, that's actually a pretty cool trick. So what you can do is you can say iterate over the spans and we zip and skip one, right? So we can create another iterator and we skip one. So now, wait, why do you not like this? Not spans. And now we get access to all the spans. Is that a problem? I guess we could miss out on the last span, right? Yeah, let's just enumerate here. I think that's a little easier. So I can like say that last is equals to spans get index -1. Okay, it could probably be an issue. Okay, we could say like, if index is greater than 0, let less is equal to spans get -1 unwrap. Okay, that's fine. So it's like that diff band start slash end. Exactly. Literal push string. Repeat diff. Cool. And then we just push literal. So that could make the tests pass, right? Maybe. Okay. Cool. Expected type input unresolved. Can I see why is this not correct? Expected type int found unresolved. Okay, that's actually interesting. Because we should resolve the type of B first, right? We do set the type of B, do we? I hope we do. Let's see. So that would be in our, let's say, declare variable. So we should do that. Hmm. And so when we go into our variable expression, we set the type of our expression. Okay. This is actually weird. So it says undeclared variable a here, which is correct. This should not be an error. Expected. Found unresolved. Why? What? That's actually interesting. Okay, let's see the other things. Okay, I mean, that makes sense. Failed to compile, yeah, okay. Parenthesized binary expression. Okay, that also makes sense. Okay. Nice. So yeah, let's just, I don't know, let's just add a type resolving to all the other expressions and let's see if that would fix anything. I guess we could write another test here for unary expressions and should report type mismatch when using minus unary operator on bool. Yeah, I guess something like that. We probably have to add tests for every operator here. Probably could also kind of automate that, right? Yeah, let's see. So binary expression, we have done that. Boolean expression, unary expression, we have not done yet. Let statement, we have done. If statement, we have done. Block statement, where we don't need that. So let's just see, what else do we have here? Visit parenthesized expression. Can query that and set the type. Right, cool. So this should fix at least some tests, right? Yep, okay, it did. So this, why does this say undeclared variable a? What? Oh, okay, I see. Like, that's actually an interesting bug. Because when we say, like, true and minus a, if we parse this as a primary expression and then look for a binary operator, we find a minus, right? And now our parser thinks that this should be a binary expression, which it actually should not be. I mean, we probably also could parse like new lines or like Lex new lines, and and then just skip new lines after each statement, right? Or we could check if there's a new line, because then if we check if there was a new line here, we'd actually find one and not find the minus next. So this would not be parsed as a binary expression. So we still have a problem here with our b. Okay, which probably results because from using a unary expression here. And same thing here. Okay. So that should fix itself once we add type resolving for our unary expression. Yeah, okay. So now we have to resolve unary expressions, which will follow like the same pattern. Maybe GitHub Copilot can even do that for us. Can we not have a plus and not a not? And no not right now? Okay. It actually did. That's pretty cool. As private, make public. So now this should fix a lot of tests. Cool. And now the only thing that fails is this, which makes sense. And we'll fix that another time, I guess. And now we probably also have to parse the types for our parameters. And I guess we will have to enforce static types for now because we don't have like advanced type inference algorithms that can detect like, okay, this function there is called with an integer, so we say, okay, this needs to have integers as parameters. So we'll probably need type annotations here, and these we will have to pass. Pass first. So how should they look like? What we could do is something like this. So TypeScript style, Rust style, like every modern programming language, basically. I think I like that. We could also do something like this, which looks spacey. I don't know. I don't think we will do that. We could also do something like this. It's kind of verbose though, right? I think we'll just go with colons for now. Yeah. Okay, and actually let's write another test that also tests for like call expression types. So like it should report type mismatch when assigning function call result to variable of another type. So this will basically test like many things. Like, okay, we can say input, and this will be something like, yeah, exactly. So we have like a function which will just return integer, and we will have like a variable b, which is of type boolean, and then we say, okay, we'll try to assign this here. We'll probably also move this the span, make it a little bigger. Yeah. Expected type bool found int. Like, yeah, I don't know, like cannot assign value. Let's just keep it simple for now. Okay, cool. Like that tests a lot of stuff actually. It tests if we have parsed this function return type correctly, and tests if assignments are properly handled when type checking. So this is cool. This is cool. I could also do a test for function parameters, I guess. When when using binup on incompatible types in function params. Really great name. Like something like this. Say like func. Yeah, exactly. A plus b. And this should return an error. Expected type int from bool. Cool. So this will also test if we have parsed those correctly. And next thing that we probably want is and should report wrong return type. Yeah. Expected type int found bool. And also what we should also do is like and should report cannot use return outside function. Yeah. I mean, that's all I want to test for now, right? I don't know, one thing. And should report type mismatch when assigning wrong type to variable with static type. Yep, that's exactly what I wanted. Nice. Okay, now this will go horribly wrong because we don't have, even lacks this colon, I think. Yep. Okay, cool. So now let's select this stuff first. Lexer? No? Okay. Probably could also move this text span to our text module, I guess. Actually, let's do that. Move file. I don't actually want to move the whole file. What? Okay. So I want to move you to text / span. Oh, okay. I guess we can. That's okay. Span. So now let's see if we can run our program. Okay, cool. So let's get into lexing once again. So what do we need? We need colon, right? And we need kind of arrow, maybe? Yeah. Right arrow. Okay. So now we have to lex this somehow. So we're gonna say, okay, colon is pretty easy. And like when parsing a minus, we can say, okay, when the next token is like this, we can say arrow. Right, okay, cool. So this will relax now. And the next step is parsing. So, first things first, probably also, yeah, we have to change our node struct. So in a function declaration, our parameters now also take an optional like type. We could probably call that like type static type annotation syntax or something like that. It's like abstract static type annotation. Like pub colon pub type name colon. Right. Which will probably for now also only be a token because every type is just an identifier because we don't have like array types or generics and stuff like that. Yeah, and we can have an optional static type annotation here. And we could have a pubstruct function return AC function return type arrow and type name, right? Which is also optional. So I think that's about it. We also need type annotations for in our let statement. So where are you? Let type annotation. Cool. So what do we need here? We need type annotation option static type annotation. No such field. Why? Return type. AST function return type. Return type. But we will need that in our let statement, right? So type annotation option static type annotation. Cool. So now let's parse this. You can just say parse optional type annotation. Current kind colon. Yeah, makes sense. Yep. So we'll probably need a constructor here. Cool. Now same for our declaration. Let's see. Parse optional return type. Arrow. We can soon check arrow. It's not going to be type annotation, but like rather an AST function return type. We'll probably also need an application for generate a constructor. And type name. So this will be type name and will be arrow. Cool stuff. Now when parsing our parameters, we'll probably also need
Bist du da morgen oder?
Nö.
Was?
Nee.
Ja?
Nein.
Nein, in der Arbeit.
Ja.
Also ich war auch so, glaube ich.
Okay. Toll. Was? Okay. Where were we? I think we need to parse our type annotation. Right. Parse optional type annotation. Actually, no. It should not be optional. So type annotation. Turn sum. Okay. Cool. And have this unit parse type annotation. Clone. Okay, you don't like this. Okay, you should not be optional actually. Cool. Now the test should run. And at least we should cannot use return outside a function, expect expression found in a file. Okay. Expects 2 arguments, but 1 was given. Okay, that's actually true. Yep, need that. Oh. Okay. Cross function call expression. Need types here. Okay, why do you not parse? Expected type in. Unresolved, okay. And I need that as well. Cool. Show report cannot return to the function. We have not implemented that yet. Expected expression found error. Okay, something is not quite right in our function declaration parsing. Parse function declaration. Parse. Okay, so we have to parse that here. Well, okay. That will make things a little easier. Okay, now the test passes. Okay. Expected found colon. Okay, so probably something wrong in our let statement parsing. Yeah, we have to move this here. Okay, okay. Expected 1, found 0. Okie dokie. So now we have to go back into our resolver. And when visiting our function declaration statement, this could actually be a problem. I guess. So the problem that could occur here, let's just write a test for that, or maybe we have even written a test for that. So essentially, the problem is that when we call this function here, then we have not yet gone through this. Okay, maybe it's not. No, that's not a problem. Okay, I think I'm dumb. I don't think that's a problem. Okay, it's fine. Yeah. And should not allow addition with void type. Right. So if you don't have return anything, you should return void. Strict int font void. Yeah. Okay, that's also something that we should do. Add a void type. Right. Now, when we visit our function declaration statement, we now don't have to set this type here, right? But like rather have to parse the token. And that's actually another test we could write, because we have to test if like an invalid type is recognized, right? And should report. What am I doing? Should report invalid, like undeclared type. Undeclared type B in let assignment. And also in parameters. Yep. Cool. So what can we do about that? We can say we have somehow to parse the type, right? So I mean, this is just a primitive type. We'll also allow for like adding custom types later. Now we can just say like type, can say and like from string. Yeah. Yeah, actually we can do that. And now in our resolver, we can go, you can say that type equals to type from string. And I guess this should return actually an option. So parameter, type annotation, type name, span, literal. So now we can match this type actually. Can I say, maybe we could just return unresolved for now. Yeah, no. Let's just do that for now. So if we have none, we just return. Yeah, we report unknown type or undeclared type. Undeclared type. Type name. Span literal. Just parse type name here, okay. Not unresolved, but like rather probably void, right? So I'll also add void here. Void. And add that here. And else we'll just say, okay, cool. We'll just return the type. And now we have to add this error message. Report undeclared type. Cool. Cool. So next up, we should probably parse the type here as well. And in our global symbol resolver, we should probably also declare a return type. Yeah, so this declare function also take a return type, which should be a type. So we can pass this here, return type. Check to clean property, return type. Okay. And let return type from string. Like, I should probably extract this method here, or this into its own method. To like say, like validate parse or resolve type from string, right? And then we can use that, can say like self resolve. Oh, okay. Maybe we should make that a shared method. I think we could also make it like a global function, I suppose. Because why not? Oh, because we have to report diagnostics. Okay. So like a mutable reference, or like a reference to a diagnostics back cell. Yeah, something like that. Resolve type from string. Okay. Resolve type from string. Return type. What is return type? Return type. Okay. Is like match function echo statement return type. So if we have a return type, then we can try to resolve it. Expected. What? Okay, that's weird. And if we have none, then it's just gonna be void. Right. Cool. We should not move you though. We should remove the semicolon. Cool. Now we have a return type. Right. So now we can say resolve type from string. Diagnostics. Nice. And that is correct. Test should still fail, right? Because the problem is that we don't validate or set like our type for a call expression. So, actually, we could probably, should probably set like the type for this expression now, right? So we can say like that type self set type, correct, type void, and here's gonna be function return type. Clone. Nice. So now we do this. So now at least some tests should pass. Okay, cool. And actually, one test that we should also probably write is the following, and should report type message in arguments in function call. Yep. And this should probably go here. Expect type in found bool. Yeah. Okay. So now let's see how we can make those tests pass. So should report cannot use return outside of function. Okay. So that is actually pretty simple to do. The thing is that like when we enter a scope, we should probably also check if we have in a function, right? So can I say function? Just pass the function symbol here. Question remains. Yeah, let's just clone it for now. I think that should be fine. And we can just write a loop to do make reference. So local scope function. Now, when we enter a new scope, we also need to check if we have a function symbol here, and then just pass this here. Now, when we enter a scope here, we probably need to do that. Do we? Yes, we do. Like now the thing is, how do I get function symbol? Like function symbol self scopes lookup function unwrap, because we should always have this function here. Sum clone, I guess, for now. Okay, maybe let's just add a reference anyway. I think that would be better. Let's not be lazy. Now we need lifetimes once again. Yay! Cool. And now our scopes will need lifetimes. And you will need a lifetime of A. Now scopes we need this lifetime. And that is working, I guess. So enter scope, none, none, none. Cannot borrow self scope is mutable because it is also borrowed as immutable. Yeah, okay. I see the problem here. Can we just like clone the reference? Okay, so we probably will need lifetimes here as well. Go scope. Please just let that work. Phantom marker, no. atom, please. Thank you. Now compilation unit will also need a lifetime. Work. Please. Shit. Okay. Why? Associate function was supposed to return data with lifetime A, but it is returning data with lifetime 1. Why though? Declare function. I mean, we clone you anyways, right? Does that fix anything? No. That actually is kind of weird, right? Isn't it? Cannot return value referencing local variable AST. Okay. You know what? Screw this. We're just gonna clone it. Blah, 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 blah. So, where were we anyway? So we just get rid of all of these lifetimes. Cool. So there we go. Can just copy that everywhere. And now the only problem is this. Right, okay. So now we have to clone this somehow. Or we have to implement clone for a function somehow. Okay, fine. Test. And we're still failing a lot of tests, okay. Okay, we have not done that. So we can actually do that. It's pretty easy. We can just go into our resolver and like say, okay, visit return statement. And we can say if we're not currently a function is inside function, or like you could actually match surrounding function. We could say like self surrounding function. Self scope surrounding function. F help and surrounding function. Local scopes for Yeah. Turn none. If we have none, then we have to report return outside of function. And we can do that. Diagnostics back. We can say and cannot return outside function. Cannot use return outside of function. Okay, cool. Wait, have we written a test that validates if the returning value is correct? Yep, okay, we have. Cool. So we can actually add that here as well. Let's say function. We have to visit the expression anyway. So something like this, return value. Okay, so if that's some return expression, return value, we have to visit this expression. Can borrow self is mutable because it is also borrowed as immutable. Okay. That's actually annoying. Okay. Okay. Does that make sense? I guess. Set void found int, right? Error when not or when using return without expression in non-void function. Non-void. Right. Okay, cool. Now we actually kind of have to. How do we do that? Immutable borrow occurs here, immutable borrow later used here. Return expression span. Okay, I see. So can we just, like, let's say, let return keyword, something like this, maybe? Huh. Mutable borrow data use here. Self-expect type, function return type, clone. Hmm. And this would still not work, but okay, this is actually weird. What? Oh, because of that? Uh, mm, Not quite sure how we will fix that. I mean, what could we do? Can a borrow cell is mutable because it's also borrowed is immutable. Mutable borrow occurs here. Yeah, okay, this makes sense. Immutable borrow occurs here. Immutable borrow later used here. Okay, I don't see from that where it is used. So use here, here, here. What? We clone this. What does clone even do for option? Trace a copy of the value. Okay, wait. What if we did something like this? Okay, this wouldn't really change anything. Okay, we're struggling here. Cannot borrow self is mutable. Trying to understand why this happens. I mean, what are we borrowing immutably? I mean, the function. Okay. I see that. Maybe we can do something like this. Yeah. I mean, that's whack, I guess. I don't want to clone the function symbol, to be honest. Yeah, I don't know. Let's just leave it to do here. Do not clone. Cool. And we're failing more tests than before. Okay. Cannot use return. Wait. So this is not reported. What? Expected expression. Oh, I see. Right, because we currently cannot parse this. Because we don't know when a statement actually ends. I guess we should probably fix this anyway. With like new lines and stuff. Yeah. I guess we can do that. So expected type void found int. Okay. It's fine. Expected expression. Okay, so we'll leave this one in here to maybe fix this later. What problem do we have here? Found 0. Okay, because we're not validating this yet. It makes sense. Okay. So let's do that actually. So we now have to type check like on function calls, I guess. So when we visit a call expression, we have to loop over every argument. And I guess we'll not visit these if we don't find the function symbol. Okay, that's not cool. Let's say that return type, maybe like this. Yeah, okay, cool. This does not make sense. Query expression. So we have to like iterate and zip the function parameter iteration. How do we figure out? Okay, this should not be string, should be like a variable symbol actually. Like argument and param. So we visit argument, we say this is the argument expression, we say expected is param type, actual is the argument expression type, and this will be span. Okay, that's fine. Now parameters, okay, strong, the okay. Yep. Parameter, type notation, type name. Nice one. Cool. Expected string found. Variable symbol. Okay. So we can actually also zip here, right? Like function parameters. So we have like argument and like parameter name is name, like clone actually. Yeah, okay, that works. Because it is also borrowed as immutable. Immutable borrow occurs here. Function. Okay, because we're using a function now. Yes, we'll probably have to clone that. It's pretty annoying because we don't actually need mutable reference here, right? Okay, we do actually. Okay, so once again, same thing here. We have to map this, clone the function. I mean, I don't like this to do not clone, but it's necessary to work, I guess. Okay, this error. Okay, assign. Okay, we do not validate assignment just yet. Expected, right? Okay. Okay, let's actually do this first. So we go into here, say visit let statement in our resolver. Resolver. Okay, maybe not there. I think we have to split this file anywhere. It's a little too large actually. Here. Okay, here we go. So there's a let statement. Now let's see. Could say like if let some type annotation is equal to let statement type annotation exactly, and then we expect type. And we select right. I transform that to a let match statement. Yeah. Nice one. Cool. Maybe we test passes now. Okay, fine. So we fix one test. Now, next up, we should probably do like assignment. Maybe get a callback can do that for us anyway. So we visit the expression, Then we say, okay, value expression, and it's gonna be query expression, and you say identify, we look at the variable. If not, we can just report. Okay, we did not actually have this test, right? Should report error when assigning to undeclared variable. Exactly, undeclared variable A. Thank you very much. Okay, and then this will be type void, probably. Yep. Expected type found in variable symbol. What is type anyway? Okay. Variable. It's like a variable type clone. Cool. Yep. Expression ID, right? Cool. Maybe one failing test less. Yep. Nice one. Okay. Now, okay, we still have the same issue here, I guess. Undeclared type B. Expected one diagnostic, found two. Okay, that's actually interesting. Wait, do we validate this twice? Like once on our global symbol resolve run, I don't know, and once on the like second pass? Could probably be an issue. Let's see if we do that. So we visit a function declaration statement. Actually, we do not do that. We enter the scope. We look at the function. Revalidate. Okay, we do actually. For resolver. So wait, why do we need to do that? I think we don't need to do that. We just can do over function symbol parameters. Then we don't need to do that. We can rather declare the variable and we're saying name, and the type is saying type clone. Borrow moved value. Oh, that's unfortunate, actually. Should clone this here then, clone this here again, I guess. Okay. One failing test less. Cool. Now, okay, yeah, same issue. Undeclared type, expected type void, found int. Okay. Expected type void, found int. Probably don't want to report an error there. Right. Expected type void. Okay, let's see. Let's see what we do here. Like maybe instead of like returning saying this returning void there, we should probably expect like anything, right? Because we don't really care. Could probably do that. Yeah, I guess. So the problem is that when we visit our let statement here, we say, okay, if we have a type annotation, we expect the type of the variable. And the variable is a void type, which happens if the type is not defined, right? If, like if we resolve this type from a string, I guess we could like return arrow here. So we could add a new type, say like arrow, and I don't know, arrow. Could never happen, like maybe add a question mark here. And yep. And so when we say is assignable to, I think when we say type, one type is arrow, say true. Of like the other is arrow, then we say true as well. Maybe that should fix that actually. And it did. Okay, that's cool. So now the only two tests that are failing have nothing to do with type checking anymore, but like rather with how we parse statements and use separators, because at the moment we actually don't, and we probably have to respect new lines to actually make something like this work, because right now new line is just discarded and we think this is a binary expression. So expected type void found int. So we actually have to provide a return type here, right? Cool. So I think we have gotten pretty far today, actually. And I'm pretty happy. So what have we done today? We have implemented pretty cool type checking. So for example, let's write a little program that maybe has some type issues, you know? Where we say, okay, like func add, and we say like A and B. So we're missing, at least for here, we're missing a type annotation. And we say, okay, we forget to specify the return type. And we say return A plus B. Now we say, okay, let A is equal add 1 and 2. Then we try to assign, they say, okay, but I want A to be a boolean. And let B should be like true plus A. And then we'll say like while A is, wait, A plus 1. Something like this. Okay, let's see. Okay, and we get lots of errors. Okay. Let's see. This is also a problem that we currently have. Like our parser. Oh, hey Frosty. Yeah, we're having a good time. I guess we've just implemented type checking, and it's really cool. So you can like, wait, let me show you. Something like this works now. And we can say like, okay, we get an error when we return A plus B because we have not specified a return type here. So it says expected type void and found int because A is an integer and B is an integer. So we say A plus B, which of course evaluates to an integer as well. And so that's an error. And because this returns void, A is of type void, and we try to assign bool to it, and that should not work. So it gives an error like expected type void, but found bool. And same here, because we cannot add like a boolean and integer, so it just says expected type int found bool. Same here, because we can not add int and void. And yep. Also, I don't quite understand why it does not give an error here, because this obviously is an integer as well. And you should be a boolean in here, right? Maybe because we have an error in this expression, so it just is smart enough to not throw another error that has to do with the same error here. But the problem that we currently have is, for example, leave this type annotation out, we just get a whole bunch of errors. Like, you see this? Like, Jesus. And that is because our parser is not really like error agnostic. So when we have like one issue in our program, syntax wise, it just doesn't recognize that and just tries to parse straight away. And so it, because we expect something like this here, it expects a colon here, does not find one, expects a type here, does not find one, and it expects a comma here, does not find one, and so on. And so that is a problem at the moment, and I have to kind of think of a solution for that. I don't quite know how we will solve that yet. I mean, we could probably like check, or like, if we know that there should be two tokens following this A, and there's the next token is a comma, then we just don't try to consume two tokens and just report one error. Something like this, maybe. Yeah. And let's see if this works. Like if we say, actually we return an integer here. So A is now an integer, and we just remove B. Now this should give us an error because this is an integer. Let's see. And actually does not. Which is kind of surprising actually, and we just run into an infinite loop here. Okay. That's actually funny. So we'll fix that. Guess just write a quick regression test. Oh, because it's a while loop, right? I think we have not implemented type checking for a while loop. And should not allow non-bool types in while condition. So, expected type bool found int, right? So let me copy that. Nice. Okay, now this is failing. Now we have to add type checking to our while statement. So to do that, we have to go into our resolver and visit our while statement. Right, so we visit the condition, then we query the condition from our AST query expression, and now we expect type bool. And this is it. I think it has to pass now. And it does. And let's see what happens when we run the program now. We get an error. Expected type bool. Found it. It's pretty nice. Okay, so our printer does not print type annotations here. I think we could add that. So, it's the wrong printer. We need this one. So like, we have to do this in our let statement. Right. So we can maybe even extract that into its own method. Which color should we choose for our type? For types, type color light blue. Okay, fine. GitHub Copilot rules. Add type. So we can like say, I don't know, write at type annotation. Type annotation. I think we call it static type annotation, right? So we add a colon, right? A white space, and add a type, which will be this one. Cool. So now we just have to use this. Let, so if let's type annotation. Right, exactly. So this is being used here now. We also have to add that to our function declaration. White space. Yeah, I guess. Self at type annotation. Parameter type annotation. Nice. So now let's see if this is being printed. Yeah. I love like the coloring in IntelliJ. It's just like light blue and it's like orange. That's hilarious. But it's working, I guess, which is pretty nice. And let's try to actually add a static type to our let segment here. Int run. Okay, it's also highlighted. I don't think we need this white space here, right? Visit let's. I guess we don't want to add this white space if we want to add a type annotation. Like add this here and don't add this. Nice. Okay, cool. And so, for example, if we said static type should be bool, we would get errors here because we cannot assign int to bool, and we cannot add an integer with a boolean, and so on and so on and so on. And we even get an error when we say like blah blah blah, because this type is not known, right? It's not declared. Undeclared type, whatever. And expected type bool found int. I don't know why this evaluates to int. That's actually funny because it's just random stuff plus an int. What happens if I do that? Okay, doesn't give me an error for that, which is probably nice because we don't want cascading errors, I guess. Yeah. So that's where we currently at, right? And this actually throws an error, which makes sense. We run into an infinite loop here. Okay. Cool. Wait. Does that even make any sense? Yeah, okay, because we have a value and this value is 0 now. Okay, makes sense. So if we say a here, at the end it should be 3. Okay, nice one. So I think this is it for this stream. I don't know, Frosty, if you're still here, maybe give some suggestions on what we should do next. I think we have written down like AR lowering and maybe like adding strings. I think that sounds like a plan. Maybe we could do something else if you have any suggestions. Yeah, I mean, we have some bugs to fix still, like this one, because we can't have like empty returns. And we also have problems with like parsing Uran expressions on a new line. Yeah. Cooler. So I guess we will add lowering in the next stream. Yeah, I think that sounds like a plan, right? So we will try to lower our higher level constructs into something that our computer can understand, or like is more likely to understand, or is like closer to the actual assembly representation. So yeah, I think we will do that next stream. Like we just try to get everything into like a single instruction stream where we don't have like nesting and stuff like we currently do. So we just have one single stream of instructions. I think that's a plan for the next stream. Or we could add strings. I don't know. Frosty, you can decide. Do we want to do IR lowering or add strings first? Because I don't really care, to be honest. I think what else we could do is maybe add like file reading, so we don't have to type our input in here. We can like type it into an actual file. Shouldn't take too long, I guess. Yeah. Else could we do? Mm, maybe something like support for multiple files. I don't know. I don't think that makes any sense before like actually doing lowering. I think I've just thought of a bug that we might have. Just looking at this. I think something like this won't work. And it should probably, right? Because we can have a forward reference from inside a function to a global variable. I don't think that's gonna work, right? Yeah, it just says undeclared variable a. Hmm. I think that should work. So let's add a test for that so we don't forget. Or we could just fix it right now, actually. Hey, nice. So this will fail. Yeah. I guess what we could do probably is something like the following. We could also visit let statements in our global symbol resolver. Right. I guess we could do that, yeah. We could extract this like resolve let statement. The problem is that we do not share code between our global symbol resolver and our resolver, right? Hmm. So how do we reference this method from a global resolver? I mean, could maybe just extract that into a global method. Global function, I mean. Just say diagnostics, just be a reference to diagnostics backsaw. Like this. And we'll put you here. Like say expect type. Diagnostics. Yeah, something like this. Okay. And now we can try to extract the resolve that statement function, that statement function into a global function. So we'll just take this. So where do you want to put this? Like here, probably. This will need a reference to an AST, blah, blah, blah. Diagnostics. And a mutable reference to scopes. Scopes. Oh, and probably also have to visit an expression here. Okay, it's getting a little bit more complicated than I thought. Visitor. Wait, what am I even doing? Okay, fine, cool. Hey. Maybe we could also like just implement a trait that has these methods. I mean, it's fine for now. So, expect type. Right, okay, cool. So now we can implement this method on the resolver. I guess. Where's our implementation block for resolver? Here it is. Resolve let. Okay, how do we do that? The visitor does have to be immutable, right? Okay, that's actually interesting. Oh. That's actually kind of annoying, to be honest. Okay, screw it. To be honest, I think we will just copy and paste it for now. So I don't want to waste too much time on this now. Oh. Right, okay. Let's just take this and paste it here. Oh no. This is so bad. Jesus. So, but if I think about it, to be honest, I don't even think that makes too much sense. Because now you would also allow forward references between global variables. I don't think that doesn't make too much sense. Does it? I don't think it does, actually. Yeah, maybe let's just not do that for now. I guess we could also remove the test. So just some time wasting here. Yeah, it's fine. So we have something to do for the next stream, which is IR lowering and fixing issues with like new line separators. So we got pretty far in this stream, and I'll see you guys in the next one. Bye bye.